system telling me that somebody will be removed, but for whatever reason I will. So Fatin already got removed by the system for reasons that I'm not so sure why. So try your best to get back in, and somebody else accept Fatin's entry in this session. So without further ado, I would start with the lecture. So okay. So as I said to you just now, today we're going to concentrate on cation exchange capacity, and I am going to focus on the chemistry and also calculation. Now, frankly speaking, cation exchange capacity, after this, I'm going to call it a lot with CEC, the short form, CEC. So don't be confused, like it's actually meant cation exchange capacity. Now, first of all, this CEC value is closely associated with soil fertility. However, being an environmental scientist like us, soil fertility is just part of it, because we also learned long before that soil has the ability as sorbent. And in order to tell which sorbent is stronger, it's also come back to the same thing. How much CEC do they have? Actually, the higher the better. Okay? So the higher the CEC, the better the soil as a sorbent to remove pollutants from somewhere else. Yeah? Okay, so today's lesson, let's go through the outline, introduction, plant nutrients, soil, source of elements in soil, soil colloid. So soil colloid, we're going to talk a lot about clay and also those suspended particles in the liquid form. Cation exchange. So there will be a lot of chemistry involved right here. Then we move on to cation behavior and the exchange side, in which these two we're going to learn a bit more about calculation, how to calculate CEC, and then the rest will take place lah. Anion also will be part of, even though this lecture is about cation exchange capacity, but anion storage we're going to touch a little bit. And the rest of it, application of CEC, why it is so important. In fact, CEC can be said to be the single most important soil parameter, an indicator how good is the soil or how healthy is the soil, apart from the pH that we learned yesterday. Okay, now this one I'm not going to talk too much about this one. You can read it by yourself. But to sum this up, cation exchange is a measure of soil fertility, because when a soil have a very large capacity to absorb cation, it is said to be very fertile. Now, why this is so? Because if you look back on what are the nutrients that plant use, most of them actually appear in cation. Very few are anions. So cation, to come back, is actually some particles, charged particles, which is in positive charge. So cation is positive charge, anion is negative charge. The more the soil can trap this positive charge, meaning that most of the nutrient can be stored in the soil. So that's why they're so good. Now, there's one more thing that you need to remember also. Storing also is one thing. Releasing it is another. So after this, at the bottom of this slide, you can see bioavailability. Now, bioavailability means how well this cation can be absorbed by plants. Not just plants, it could also mean bacteria or any organisms. That means how easy this nutrient can be taken by any organism from the soil. And usually that won't be such a big problem. It's usually whatever that is absorbed by the soil, most of the time they're accessible. But there might be a small part which is not bioavailable. There might be. So if you detected that the soil have maybe 1 gram of potassium, for example, not the entire 1 gram can be absorbed by plants. That is a fact. Why? If you still remember last time we learned about pore, remember micropore? Yeah. Whatever the nutrients that end up in micropore, those usually are not available. But when we learn about this one, usually the cation exchange that we learn today is referred to the available ones. Okay, you probably still don't get the idea, but don't worry. So later on, when we go into the lecture, then I'll explain further. Okay, why I said so. So we'll begin with plant nutrients. Now, if you still remember what I've taught earlier about introduction to soil, I informed you that there are macronutrient and there are micronutrient. So no need to tell what are the consequences if these plants lack of any one of these elements. Something bad will happen to you. Something bad will happen to the plants, isn't it? So I think I'm going to go straight to the nutrient. Now, among all these nutrients, you can see the macronutrients are listed right here, apart from NPK. N means nitrogen, P, phosphorus, K, potassium. There are many more actually. Now, we do not list carbon, oxygen, and hydrogen simply because carbon can be available. It's always available due to global warming. Why not? Because carbon dioxide. This is where carbon is taken from the air by plants. Oxygen also from the atmosphere. Hydrogen is from water. So as long as you have the atmosphere and also water, the plant can survive. Uh, but with the condition that they also need a few more of that. There are also the other macronutrients, that is nitrogen, phosphorus, and potassium, and NPK, as I said earlier, plus calcium, magnesium, and sulfur. Now, why sulfur is here? Because you remember protein. Protein is made partly by sulfur. Calcium and magnesium, they are the structure of the cell wall. So the plants, without too much of calcium, magnesium, they look very limpy and soft. So this is why. Anyway, we talk about human. Calcium and magnesium also is the bone structure. So they are mostly involved in structure formation. Now, in terms of the quantity that is needed, there's no doubt nitrogen is still on the top. Because why? Again, nitrogen also involved primarily in the protein formation. So the enzyme, yeah, the enzyme, sometimes, occasionally, the structure may also contain significant amount of nitrogen. So those are macronutrients. As you can see right there, the beneficial elements. Some are essential, some are non-essential. Non-essential usually referred as toxic non-essential elements. However, let me remind you, even though there's so-called essential elements are listed right here, doesn't mean that they cannot be toxic. There's one way they can be toxic, if their concentration is too high. Yeah, if the concentration is too high, for example, zinc. Zinc here is an essential element. However, they are micronutrient. Now, zinc is only needed in small quantity. I forgot what is that for. I remember zinc is probably used in manufacture one of the enzyme for living organism. However, if zinc, if too much of zinc is available in the soil, this itself serves as a herbicide. It kills the plant. Plant cannot grow if too much of zinc. Similarly for copper, nickel, even worse. Yeah, and sometimes iron. Can you believe it? Iron itself, like, is so natural. There's so much of iron in the soil because, as you see, the clay soil that you see from the forest, they're all red in color, isn't it? That is because of the presence of iron. How does iron kill plants? Now, when I studied in Australia, I remember there's one herbicide. It's iron chelate, they call it. Yeah, it's just iron, red color, and also some chelates. Now, chelates is simply something equivalent to citric acid. Okay, I think I've talked enough about chemistry, and then I think I should move on. Now, to recap just now what I said to you earlier, micronutrients, they are needed. So these are nutrients. These are elements that are needed in trace amount. Trace means extremely small amount. Yeah. These are the summary of the essential nutrients in macro and micronutrients, which you do not need to memorize. You don't need to memorize. Just have a look, but don't mess up, really. I mean, I don't expect you to memorize all these nutrients, but at least you should know what is NPK. NPK is part of the macronutrient. The rest of it, common sense, lah. Yeah? You don't see lead, you don't see mercury, you don't see cadmium. The rest of it, almost everybody is here. So small amount, they are micronutrients. And let's not forget calcium and magnesium as well. So what will happen? Oh, do you see anything similar here? Yes, isn't it? You see the leaves. The leaves, all of them are yellowing. We have a term for this one. We don't call it yellowing. This phenomena we call it chlorosis. Chlorosis. So you can Google after this what is chlorosis. Chlorosis means the loss of chlorophyll. So exactly what happened. Because of the lack of the chlorophyll, the green color will fade away and that leaves the yellowish color. It's not that they show the yellow pigment, but they are losing the green color pigment that gives you the yellowish color. Okay, so nutrients are important and they should be supplied to the plants as much as we can and as available as they can in the soil. Now, where do we get this element in the soil? Now, I think this one has been discussed earlier, right? Like where is calcium is found usually in minerals, potassium maybe, but potassium also may be available in organic matter. And how do they like release uh, mineralize into absorb nutrients and also dissolve ions. I think this one I've covered earlier. Exactly like this. Did I? Okay, I think maybe you can switch on your microphone. Did I actually explain this one? I think I did. Yeah, someone? Did I actually explain this one to you?
I think it's no.
Yeah, haven't. Okay, I haven't. Okay, now. All right, thank you. Now I will going to spend a little bit of time talking about this one. Because why? When I look at this diagram, I can see one essay question. It doesn't mean that I'll give you one essay question because why? There's no final exam. Don't worry. Your question in your test will be in objective base. So impossible I can give you essay question right here. However, if you're talking about soil and soil science, this is very, very important. So I'm going to spend a little bit of time explain to you what exactly happened. Now imagine that when Earth is first formed, usually they form rocks, isn't it? Mineral, sedimentary rocks, igneous rocks, or whatever. They started from this point. So the origins of all these mineral or all these elements, they started with the rocks. Now rocks, as time goes by, with weathering, with all the climatic elements like the heat and also the moisture, the precipitation, slowly they become dissolved. But first, these rocks will be broken into small pieces, maybe to gravel, to sand, silt, and finally clay. And when they are being broken, at the same time, they will release a little bit of this nutrient into liquid phase in a form of dissolved solution. So, like for example, calcium. Calcium is so easily dissolved in normal rain because normal rain, the pH is usually 4.5. So they actually can dissolve a little bit calcium and they flow. They follow the direction of rainfall, like runoff. So they will going to end up in soil solution. This will be the moisture that is trapped in the soil, or maybe if it's a heavy downpour, heavy rain, they will going to flow along with the direction of the runoff along the surface. Now, if they are being absorbed in the soil, there are plenty of things that will happen. However, before I continue to the next part, there will be a reverse of this one. Now, if any minerals can dissolve, surely they can be fixed and reversed back into mineral phase. Now, coming back to the example just now, calcium, limestone, for example, calcium carbonate, they dissolve with acidic rain. But of course, this pH will not stay forever because neutralization gradually will happen. Now, if that happened, or maybe due to evaporation, when rain becomes evaporated, they will slowly crystallize and it comes back to calcium carbonate, limestone. So it's a two-way reaction actually. Okay, now once these elements are dissolved in soil solution, it may become an organic matter. Now, from solution into organic matter, it will be some active uptake. That means this organic matter, whether it's a dead organic matter or still a living organism, it still have something to do with some active uptake. Active uptake means, like for example, the nutrients are dissolved in soil moisture and they are being absorbed by a living plant. So that is a active uptake. Yeah. So it involves some energy from living organism absorbed into the plants and then assimilated, and it becomes part of the plant. Well, of course, part of the plant, it could be the leaves, it could be twigs, some tree branches, even the roots itself. So these are part of the organic matter. So you see, the nutrients that they got from the dissolved minerals earlier, they may be accumulated in the plants, and when these plants die and then they end up on the surface of soil, organism eats them away, they may going to re-dissolve again in the soil and come back to soil solution. So you see, there's a living things going on here, and usually it involves plants. Yeah. Now the name itself, from from here to here, from a solution, from soil solution, it is uptake by organic matter. Let's say if this organic matter is a dead organic matter, non-living things, it will be called immobilization. Now, immobilization simply means that something that are suspended or locked near the surface or in the bodies of this organic matter. It could be adsorbed, it could be absorbed. Adsorb means adsorb means it end up on the surface of this organic matter. Absorb means it comes into the organic matter. So there are some difference lah. Immobilization, it could be these two ways. However, if it comes back to, if it's degraded by a microorganism, decompose and then return to soil solution, this is called mineralization. So mineralization means the release of the earlier immobilized elements back to solution. Now the next one is adsorb on soil colloid. Now this one is a bit different because this one does not involve living organism. Now soil colloids usually refer to clay. Now colloid, for your information, can be more than clay. Like for example, the milk solution also can be called a colloid system. However, milk does not have clay. What's in the milk? They are primarily protein. Protein is not clay, kan? Protein is organic. Clay is inorganic. The appearance more or less the same. So what do you call colloid? Another name to replace colloid is suspension. Okay, so if you like to jot it down, yeah, there is another name for colloid. We call it suspension. Now this system is indicating something that are like so well mixed with liquid that they appear that they mix very well. However, that they don't dissolve. So this is a key word. They can mix very well, but they cannot dissolve. These kind of things, this kind of situation, usually you're going to produce a colloid system or suspension. Okay, now between soil solution and also the clay, there's only one thing happen: cation exchange. Now, when I say cation exchange, there's only one reaction. It's adsorption. AD. Well, in fact, this box already tell you that adsorption. Now, adsorption is from solution to this soil colloid. What about the release? Well, the release of it also can be called a cation exchange process. Now, later on, I'm going to give you a diagram on how this reaction happens. However, when we say exchange, yeah, that means, let's say, if one potassium comes in, one hydrogen maybe comes out. Something that they trade off, yeah, in and out. Now, usually when there's a final exam, I usually are going to tell the student, hey, they are like so nice here. 4 boxes with 5 names. In fact, if you remember, every time we give like essay question, we usually have like 8 points. So this fits all the criteria. I managed to give one question before, but they failed to like explain. Well, previous students, they have no problem memorizing all these names. They can memorize all these names. However, they cannot explain what exactly here. Now, unfortunately, I have to tell you that this is part of the intended learning. So these are the language of chemistry and also soil science that you need to know, and better still, understood. So if you don't understand, then there are a lot of videos you can see. What is fixation, solution, immobilization, mineralization, and cation exchange. Get yourselves access to this video, have some idea how this happened, and better still, have the language skills to explain. I know a lot of you can explain really well in Bahasa Melayu. However, in Bahasa Inggris, you have to find a way lah, yeah. Okay, soil minerals, I think I have talked a little bit just now. The minerals are usually inorganic. Organic matter, I think, well, I need some consensus because I believe I talked about mineral, organic matter, absorb nutrients, and dissolve ions just now. Now, I would like to stop here and ask you, does anybody here need me to explain this one more time? Do you understand what are minerals, organic matter, dissolved ions, and so on? Do you need me to elaborate? Because if not, I would like to fast forward. Can I go and fast forward? I need some answers. Are you still there? Or you rather ask question in, oh yeah, you ask question in the chat box. Okay, so far so good. Dissolved ions. Okay. So Mahira, you want me to explain about dissolved ion? Yeah. Okay, dissolved ion. Let me come back to dissolved ion right here. Okay, now dissolved ion is the most readily available form of nutrients. Now, dissolved ion is just simply uh, the elements. Like for example, just now I used limestone. But you just remember, so limestone is calcium carbonate. They are in solid form. Okay. Now, in order to become a dissolved ions, the easiest is you just mix with some acidic water. So that reaction neutralize the alkali, and then they'll become a dissolved nutrient. So I think it's easy as that. However, there's one more thing. There's one more thing. Apart from converting something from solid into liquid form, these ions are usually said to be bioavailable. Yeah, so there's one more thing I need to add about dissolved ions. Why dissolved ions is so important in the soil? Because usually anything that is soluble is said to be bioavailable. So I told you just now what is bioavailable, guys. That means this nutrient can be absorbed by plants. Okay, I think I need to come back and see who else have any question. So yeah, any more question before we continue? Can we continue? Respond by verbally or typewriting also can. Can we continue? All right. So, well, I'll come back lah. I'll come back if you have any question. Anyway, so we've done with the 4 phases. Now, okay, now here is I would say the challenging part. I won't say it's hard part. It's easy for me. I'm not sure about you. Now I'm going to talk about, anyway, I think I'm going to use this one because if I can't see your response. I think I'll just carry on. Okay, now after this, I'm going to talk about soil colloid. So this is where we start learning a lot about chemistries. The structure of clay and also soil. So this is the chemistry, real chemistry of soil. For the idea, I'm going to continue. Now, soil colloid, as I told you just now, is a suspension of clay. How small is clay? I think you still remember the size, 0.002 mm or 2 micron. Now, the smallest clay can be termed as colloid. Now, like I told you just now, this clay can be as small as not really an atom, but maybe several hundred times of an atom. They can really go really small. In fact, sometimes clay is defined as a nanoparticle at times. So when they dissolve in water, they can really mix very well. But let's not forget, clay cannot dissolve. There's only one big reason. Because clay have very high, not very high, high molecular weight. So if you learned in chemistry before, anything that have high molecular weight may not dissolve in water. So how do I know if the clay dissolve or not? Simple. They don't give any clear solution, kan? So they don't dissolve. Now, in this case, usually clay, when they mix with water, they can mix really well because clay have a lot of negative charge. But at the same time, they have high molecular weight, so they cannot dissolve, but they can mix well with water. Therefore, you have the suspension, the soil colloid, we call it. Okay, important note on colloids. Some nutrients are absorbed on soil colloids that carry a slight electrical charge. Now, this nutrient, well, nutrient is a very broad word because, like I told you just now, elements that is considered nutrient, they are like 16 just now, you know, 16. So some of these nutrients may be 2 plus charge, yeah, like calcium. When they absorb into one negative charge, they might change the electrical charge to positive. So that is a possibility. And in fact, this is what this second point is meant. Okay, so get yourself ready to look at a few structures. So there are three types of soil colloids: silicate clays, oxide clays, and also humus. Okay, humus. Humus is not inorganic. Humus, in fact, if you still remember earlier, I showed you humic acid. Yeah, exactly that. Very large structure, primarily carbon. Majority of the elements carbon, but they also happens to have carboxylic acid, hydroxy group. So that's why they are like having some cation exchange capacity because of the presence of carboxylic and hydroxy group. Now you're probably not sure what silicate clay looks like. So this is it. Silicate clay, as the name show itself, silicate contains silicon, of course. But there are other elements also, and I don't think you are interested on this text because I believe in order to learn silicate clays, the best way to learn it is by looking at the actual structure. Well, still not yet the actual structure, but furthermore, silicate, as I told you, silicon consists of silicon plus oxygen element. And in fact, I would say oxygen is the major element here, or probably a little bit of aluminium. Yeah, so it consists of these three. Now, there's one keyword here which is bolded. I want to come back. Okay? A mineral silicate clay called a micelle is flat, plate-like crystal made of many layers. Each layer is in turn is made of 2 or 3 sheets. Okay, this is micelle. And once again, I don't think I need to talk too much. I just show you like the structure of myself. Still not yet myself. Now, I would like to say myself is like a sandwich. It looks indeed like a sandwich. It consists of 2 or 3 layers. Um, but each layer actually looks like a polymer. It's not exactly the polymer that you see like in plastic, but polymer in the sense that this layer in the micelle consists of very small repeating units. So as you learned before, polymer consists of very little repeating monomers. Now, if a micelle is a polymer, this is the monomer. So silicate clays. Silicate clays, this is not the only unit you see. You probably see this unit connected to each other in a very long structure. So that is how one layer looks like. So we're not talking about micelle. Micelle have 2 or 3 layers, guys. So this is just one layer. One layer, you see one unit right here. Inside here, your silicon, surrounded by 4 oxygen. Okay, so I'm going to use analogy lah if you're not sure. So once again, the layer is polymer. This one is the monomer. Now, there's another kind of layer. Now, this kind of layer, instead of silicon inside, is aluminium. Now, aluminium, in this case, surrounded by 6 oxygen. 6 hydroxyl group, in fact, not oxygen, only 6 hydroxyl group. Because each of these large white circle, they are attached with one gray sphere. So this gray sphere is hydrogen. So that's why OH, it's hydroxyl group. Now, let me come back to this. Okay, now I think I missed out 171. Now, any silicate clays that consists of this repeating unit, we call it a silica repeating unit. The structure here reminiscence of a pyramid. It's not exactly a square bottom pyramid, but it's actually like a tetrahedral, we call it. It's just like your methane that you learn in chemistry. This is the tetrahedral arrangement. Whereas if it is surrounded by 6 hydroxyl group, it's called octahedron. Familiar? Yeah, because you learn it in chemistry. Part 1 or part 2. Don't worry, if you forgot about that one, I don't think this one going to make that and made it in your quiz question or exam question. I don't think so. Because I will rather ask some other things. Okay, so you learn about the monomer, okay, the small unit in each layer. So one micelle is either one layer or one layer. What exactly is that? So this is example of one layer. See, one alumina and the other one silica. So this is one. 2 1, yeah. Either 2 sheet silica or 1 alumina. There's a possibility, but in fact, that is it. Now, if you look closely, a small section, if you can like imagine, you enlarge, you cut a small section and enlarge it. This is exactly what you are seeing. At the bottom is silica, which is silica sheet, which is tetrahedral shape. On top of here is alumina sheet, the octahedral arrangement. So this is one component, one small part in a clay or a micelle. But the question is, where is the negative charge? I think the negative charge will arise somewhere, and it has to be something that are negative. Now, in this case, there's no question. The negative charge will not come from silica, will not come from silicon, because silicon is 4 plus charge. Aluminium, I think you also know that aluminium, Al 3 plus. So you're not getting the negative charge from aluminium. So there's only one candidate, from oxygen, of course. But you see, good student, okay, a student good in organic chemistry, straight away they know where is the negative charge. Now, if not because of this online learning, I can see your face and I will know whether you understand or not. And unfortunately, I cannot do this two-way interaction with you. So I think I'm going to tell you, I'm going to break it to you. Where is the negative charge? Okay, the negative charge is at the bottom. So if you have like a note, a handout that is like physical, and you have a pen, make sure you put some negative charge over here, negative charge at the bottom of the silica sheet. So each of these oxygen carries a negative charge. So you might be asking me, what about the one on top? Well, you can see hydroxyl gun. So if this is oxygen, there's another hydrogen attached to it. And that is why they don't have negative charge. Because if they don't have the hydrogen, probably they do have negative charge. But because of the presence of hydrogen, they all are electrostatically neutral. Those gray on top, they have no charge. The only charge you can get at the bottom, of this micelle. Which is why you can see right here, it should have like a negative here. To be more accurate, like you should put a negative here, and hydrogen bond is correct. Because hydrogen bond is actually an electrostatic interaction between oxygen and also this hydrogen. Okay, so I think I will stop later. Let me finish the other one. Okay, so now we're learning one layer micelle. The other type of micelle is 2-1 kan. 2-1 is like this. In 2-1 layer micelle, you will have 2 silica sheets, and inside there's 1 aluminium. it looks just like a sandwich, except that this is very small. And once again, if you can magnify one small section, this is what you can see. Now, compared to the one layer micelle, the other side of this micelle happens to be also silica. So if you still remember earlier, only the bottom is silica, isn't it? But in this kind of micelle, both sides having silica sheet. So guess what's on top? Yes, negative charge. In fact, negative charge on both sides, on top and also the bottom. So once again, if you have a pen and you have a paper, this printed notes, you can start drawing negative charge over here. Negative charge at the bottom, negative charge on top. Okay, now moving on to this three-layer diagram. If all the entire surface is negative charge, and there comes another 2,1 micelle, negative charge will interact with negative charge through one interaction. There's no hydrogen bond. Earlier, there's hydrogen bond because right here, you have hydrogen. And guess what? This hydrogen actually is not charged, but it's also not neutral. I would say this hydrogen have a delta plus charge. So once again, if you have a pen, don't forget right here, jot here delta plus, delta plus. So earlier here is negative cut, delta plus with negative, positive charge with negative charge incurs attraction, electrostatic attraction, which they will come close together, right? Yeah. So for one micelle, usually they can come close together. Now, for 2,1 layer, each of these micelle, 2,1 layer micelle, they have negative charge, negative with negative. They repel. So the interaction here is not just no hydrogen bond, it's repulsion, because here you have negative, the other side you have negative, it will be repulsion. So they're not only not going to come close together, they might repel as far as possible. And because of this repulsion, any clay that is under the 2,1 layer system, 2,1 layer micelle, they usually will form suspension in water. Very simple. You just take any clay outside in the soil, you mix with water, you gochang here, and then it become like mixed very well, isn't it? And you put it aside. Even after for a while, the so-called cloudiness of water will not settle down. Because why? They repel. They keep on repelling, keep moving in the solution until they cannot settle. Well, eventually they would, but they don't settle very quickly because of this repulsion. Yeah. So because of this repulsion, they also suspended in the soil for such a long time. Okay, let me check back at the time. It's already half an hour. So I think I'm going to stop here for a while to check back with you to see if anybody have any questions so far. Oh, the wind sound. You know why? Because I have a fan just beside me and it's hot over here, you see. So what do I do? Give me a minute. Okay, let's take a 5-minute break. It's already about half an hour. Let's take a 5-minute break and let me readjust my fan. After this, but before that, is there any questions so far about the structure? Any question? No question, right? Okay. So we're going to come back after 5 minutes. Let me readjust my fan and let me know again if there's any distraction from the noise of the wind. Yeah. Okay.